ready for some language creators? Okay. Without further ado, I will introduce Carol Willing. She is a Python Steering Council and Project Jupyter Steering Council member. She blends the strengths of Python and Jupyter notebooks to improve access to learning and education. Due to the worldwide foundation of the Python language, the hard work of the Jupyter team and users worldwide, Carol was awarded the 2017 ACM Software System Award, recognizing the lasting influence of Jupyter, a broad collaboration that develops open source tools for interactive computing with a language agnostic design. Thank you.
Welcome everybody for being here. It is my absolute pleasure to share this evening with you and some of the people that actually influenced my career in software development. So let's get through this. And for those of you that are watching us on the live stream, hello and welcome. And we hope you have a wonderful evening with us. We have a really distinguished panel of language creators, and I'd like to invite them to the stage as they read their bios. I'm going to keep the bios really short because I think most of them need no introduction whatsoever, and that'll save us some time for more juicy language design stuff. Okay, so first we have Guido van Rossum, who developed the Python language that touches pretty much every corner of society today in some way, and Gosling is the creator of Java, which is used across a wide variety of devices and deployments at scale. Welcome, and please join us. And there's Hejlsberg, who has architected a number of languages over the past several decades, including Turbo Pascal, Delphi, C#, and some of you might know this little language, TypeScript. And last but certainly not least, Larry Wall, who combined his unique perspective on text and computing with his strong background in linguistics to create Perl and its sister sibling, Perl 6. Welcome. So, just a couple housekeeping things about this evening's format. You're in for an engaging and hopefully very lively discussion, more lively than we were at dinner. I think that's possible, right? Okay. The format for the...
More beer.
More beer. Okay, we can do that. Keep it coming. Okay, so the format will be 2 sessions with a 15-minute intermission. What I'll do is I will start by asking one of the panelists a question, and hopefully the response will be like 1 to 2 minutes, and then we'll kind of throw it open for other panelists to respond, and hopefully get a really good discussion going. And the more you discuss, the less I have to ask questions, and the more in-depth we can go on the really cool stuff. After the 15-minute intermission, we're going to take questions from the audience over Twitter. Okay, so tweet out your questions. Hashtag is PuppyBDFL. And if you can get those in by 8 o'clock, we'll kind of collate them and have some really great audience questions about language creation and language design. So I am going to invite you to sit back, enjoy a cup of strong Java, C# responses and insights, learn pearls of wisdom, and embrace the Python programming zen. Let's get this thing started, and we'll start the celebration with a question for Guido about the principles of language design. Guido, you've mentioned before, perhaps somewhat jokingly, the Harry Potter theory of language design. What is this theory, and what do you see as the key principles of language design?
You're good.
I think you're good now.
Am I good? Okay.
the Harry Potter theory of language design was a blog post that was wrote there. I don't know, but I cannot believe that every little detail that J.K. Rowling put in the first Harry Potter book was intended as some important plot point in part 6 or 7 or 8. And even if J.K. Rowling was such a genius that she had it actually all planned out, and that was who I think we found out in book 3 was actually a wizard in disguise. But in book 1, it was just like a temporary diversion during the train ride, and otherwise you didn't hear much about the rat with a finger missing. In language design, often that's exactly how things go. You choose some detail because you have to commit. You have to pick keywords. You have to choose a style of coding. Like maybe you choose indentation instead of curly braces.
Or maybe you don't.
You're a special case. But whatever you do, in some way you're stuck with that. And you find new uses of that detail that you picked before you knew how important it would be. And the sort of the craft of designing a language is, on the one hand, pick your initial set of choices so that there are a lot of possible continuations of the story. The other half of the art of language design is going back to your story and inventing creative ways of continuing it in a way that you had not anticipated.
So I think each of you have languages that have spanned multiple decades. So what were some of the principles that made you use Java?
So Java was sort of odd in that it didn't come out of like a personal passion project or something. It was from trying to build a prototype. We were trying to understand a particular domain. We have to be embedded systems. And spent a lot of time talking to people who built software for embedded systems. And spent a lot of time trying to understand pain points. What was it in the whole process for them? What was it? How things evolved, how did their systems fit into the universe? Because it wasn't, because I was trying to worry, we were worrying about things outside of data centers. And this was a project that had about 12 people on it. And my little, yeah, but it was, my little piece was sort of like, we sort of figured out that part of the problem was that C has issues, and so I started out so out of this like large pie of a project, my slice was to make things a little easier from a programming language point of view and fix the pain points that came from the programming language part. And it started out as kind of do a better C, and it got out of control. The rest of the project really ended up just providing context. The only thing out of that project that survived was Java. But the fact that it was sort of directed at a set of pain points that happened to be, about people who were living outside of data centers and people who were sort of getting shredded by problems with networking and security and reliability, and they had to build things that ran in hostile environments like in homes. Which any home with a child in it is a hostile environment.
Speaking of the hostile environments, Pearl, what were some of the guiding principles for designing Pearl? I love you, Larry.
Yeah. That helps. Originally, Perl was designed more coming at it as a linguist than a computer scientist. So I sort of almost actively ignored some of the computer science literature at the time and said, well, what can we just throw together in one pot that will work more like a natural language? Instead of putting in a campus, university campus, and deciding where all the walkways will go, we're just going to see where people want to walk, and then put shortcuts in all those places, and build it more as a network, not as a terribly orthogonal computer sciencey or mathematical thing. And that turned out to be in the right place at the right time for bootstrapping a lot of the web. It also got used a lot for system administration, and so various principles that relate to trying to provide APIs to everything, and trying to be both a good text processing language linguistically, but also a good glue language is why it was kind of very useful with HTML as text and database backends. That needs glue, and so it was in the right place at the right time. We were very fortunate to have that timing because in the 90s it became very stable. A lot of widespread use. A lot of people were, the language itself was stabilizing in the form that it was, but there were a lot of issues, and still are. And so in the year 2000, we took a step back and basically said, we're going to break everything that needs breaking. So we kind of did the same thing, as the Python 2 to 3 step, except instead of breaking a few things, we decided to break everything that needed breaking. So we came up with a whole raft of design principles in the 15 years since then. By the way, Perl 6 did come out 2 years ago. It's getting faster. And at the beginning we said we were going to do something impossible and fail at it, but it'd be a very interesting failure. And so far it is proving to be that. But in the course of in the course of that, we came up with some really interesting list of about 60 different design principles.
Which he's going to read all of them right now.
I'm not going to read them. You know all of many of them already. Kill two birds with one stone, pick the right defaults. There's lots of them like that. But we came up with some cute ones like, you think that's cute today.
What about tomorrow?
Yeah. Conserve your brackets because ASCII, even Unicode, does not have enough brackets. Don't reinvent object orientation poorly, which arguably Perl 5 did. Stuff is too strong, features for weak ones. Late bindings sometimes cause your programs to be late. But some of the major ones are, a lot of the stuff is Perl 5 just grew over time, and there were a lot of weird magical variables. I blame Chico, and so a great deal of the redesign was just saying, okay, what is the right peg to hang everything on? Is it object oriented? Is it something in the lexical scope or in a larger scope, or what is the right peg to hang each piece of information on? And if we don't have that peg, how do we create it?
That's a great question. And since it's such a great question, I'm going to put Anders on the spot. And Terrence Parr had a quote about, while programmers value simplicity, they more often value powerful functionality, and amazing one-liners, incurring the cost of complexity. So,
Works for us.
or stress. So what are your thoughts about simplicity versus complexity and some of the principles that might guide you as you develop your languages?
I suppose I was always like, in doing the language design that I've done, always like try to make it so that there's only one way to do a particular thing. A lot of languages have 4 different ways of doing something, and you pick the wrong one, and then only weeks later do you realize you went down the wrong branch, and now you got to back up. And so, but it's not always easy, right? And I think there's like often we're guilty of creating what I call this thing I call simplexity, which is sort of like you take something complex and then you wrap a simple wrapper on top of it that's supposed to make the complexity go away, but what you're really creating is simplexity. You know, it's just like a bad abstraction on top of another bad abstraction that is simpler. So I don't know. I mean, it's.
We think of that as picking the right default over the complex thing.
Yeah, but I mean, the thing about language design is like any decision you make, you have to live with forever. I mean, and in languages you can always add, but you can never take away. And so you gotta actually, as a language designer, be very judicious about reasoning over not so much what to put in, but what not to put in. Do you know what I mean? Because people come to you all the time, oh, wouldn't it be great if you could do this, or if you could do that, or you could, well, yeah, but you can't fundamentally change the nature of the beast. If you created an imperative programming language, you can't turn it into a functional programming language. I mean, you can borrow from functional programming, but it is what it is, and you gotta stay true to the nature of the beast, or you gotta create a new beast, so to speak. Yeah.
Right. Great. Any other thoughts
interrupt
about?
yet?
Excuse me?
Can we interrupt yet? Or do we
You
have
can
more questions?
totally interrupt any time.
So, Anders's sort of point about what do you leave out, and what I remember in the early days of Python's design, there were so many people who thought they had a good idea. And I wasn't always sufficiently critical to say no. And so there are a few things that didn't work out, but at the time I hadn't learned to say no. I quickly enough did learn to say no, and I sort of developed like several lines of defense. Like the first line of defense is, hey, you think you need a new language feature, but actually you can already write that in Python. If you needed a lot, write a function or a module. Well, if they say, yeah, but everyone needs that, well, nowadays we say put it on the package repository. In those days I said, well, maybe you can propose a new standard library module. That's a lot cheaper for the language design than a new language feature. And another line of defense was, well, you can actually write extensions in C or in Fortran if you really care to. And you can help yourself that. You can modify the behavior of the language in ways that aren't accessible when you just write the pure language, but you can still sort of, you can extend it in a way that doesn't fundamentally alter the core language. And if you've tried all those things and you failed, then maybe you could argue for, well, we have to change something in the core language.
I'll interrupt too. I find that whenever I get feedback on whatever it is, the programming language I've been working on, it's people come to you with a particular instance of a problem, and it's your job as a language designer to tease out the class of problem they're talking about, and then try to understand whether there's a feature there underneath that you could put in place that is broadly applicable, not just to that one problem, but oh look, this could solve this and this and this problem as well. And so you're putting in place a class, not an instance. So that's like, and if all you're talking about is an instance, then you're probably better off leaving it out. But it's a subjective thing. But one of our principles is save your money for power tools.
We actually found this in the early design of Perl 6. We asked for RFCs. I expected about 20 suggestions. We got 361. So we had this in spades. And you know, it's completely overwhelming until I hit upon this principle, which Anders alluded to, which is basically ignore the proposed solution.
Yeah.
But there is a pain point underneath. And if you look at enough of these RFCs, and they have the same pain point, there is something you should address. There's some fundamental unification you should do underneath, or something that just is clunky that could be fixed. And especially if you're doing a complete redesign, then you can think about that sort of thing.
Yeah, and working to use the word is a big deal. It's really hard. I was kind of the word Java, which ended in about 1995. You know, there were a whole lot of problems where you know, it was clear that there was a problem there. There were like 20 or 30 worldwide academics who were absolutely at the top of their league for understanding the issues. Every one of them had two entirely different suggestions. They couldn't agree with themselves. You get like 40 different people in a room from all over the world, and they've all got radically different ideas. And you know, some of them, you know, it was their thesis, or and for some of these, you know, it's actually important to do the science project. You know, so like with generics in Java, before Java was first released, it was really clear that this was like a big issue. And you know, Bill Joy and I came about as close to spilling blood on this topic as I've gotten at work. And you know, I would much rather do something, or much rather leave something out than do something stupid.
Yeah. One of our principles: plan to be smarter later.
Yeah. Well, but that means the opening answer is no.
Yeah.
Right. And one of the things that happened with like a whole bunch of different topics in the evolution of Java was that they kind of turned into competitions. And generics and closures were both probably the most hard-fought competitions with people writing PhD theses on the topic. And that's like trying them all out. And I mean, some had no shortage of smart people at the time, but it's really hard to beat, you know, a planet full of grad students.
So speaking of grad students, at some point I think most of you were grad students, correct?
Yeah. And in linguistics.
In linguistics, okay, well, okay. But at some point you all, probably 20, 30 years ago, decided, okay, I'm going to write my own language. And things were very different back then. Internet was sort of starting, maybe not even there. I think we had computers, we had phones, right? Cell phones.
Nobody cared. Nobody cared what talking about. Nobody cared what you did with the 8th bit.
Oh,
well, I think you're decades later.
But these are languages that persisted through many changes and, you know, on different hardware. When you started designing your language, what was the key goal that you were trying to meet versus using some other existing language?
Well, I mean, for me, it's never been a key goal. But I mean, one of the secrets of success is try to solve as many problems at once as you can. And, you know, if there's just one problem, there's probably an easier way than a new programming language, right? Right.
If you think that way, you'll never have a new program.
Well,
there's always a better solution.
The three virtues it depends on how much you hate chasing down memory corruption bugs.
The three virtues of a program are laziness, impatience, and hubris. It takes hubris to
The world needs another programming language.
yeah. Go look at Rosetta. Go look at Rosetta code.
But the thing about programming languages that I think a lot of people don't realize is that every programming language is about 90% the same and maybe 10% new, if you're lucky. And a lot of people get very focused on the 10% new and forget about the 90% the same. That makes it a great language, right? I mean, there's a lot of hard, boring work in creating programming language, a lot of semantics that you just gotta worry about. And like everyone loves to talk about syntax. And syntax is the easy part. Semantics is the hard part. You know, like how the types work and what are all the supported promotions and what are the different kinds of type constructors that the language has, et cetera, et cetera. These are the hard things to design, but not the things that people love to bike shit on the syntax. You know, should it be a colon or a comma? You know, and it's like, oh my God, let's have a long thread about that.
So, talking about people having opinions and syntax and typing, these languages don't all take the same approach to typing. Maybe we'll start with Guido and talk about typing in Python and then kind of work our way around.
Typing in Python evolved at various points during the language design. I mean,
I just remember that when Python first happened, int was not a class. Int was a little conversion function. There was an internal object type, which was really just kind of a v-table that represented integer objects. And there was a built-in function if you needed to convert a string to an integer, and that was, we had a bunch of those functions. And we realized that we had made a mistake. We had given users classes that were different from the built-in object types. And for a long time it was like, oh well, like the real stuff is implemented in C. And the user writes a little bit of glue on top of that. And when I found out that we had 80 different competing web frameworks, it was sort of time to realize that people were writing much larger programs and that a different approach to types was needed. And that's where we sort of reinvented the whole approach to types in Python. And there was a bunch of cleanup that didn't happen until Python 3 actually. But one of the things we introduced, and we were lucky that there weren't actually, despite those 80 web frameworks, there weren't enough users that we were completely stymied by backwards compatibility yet, like we are now. So we just, one day we changed the function int into a designator for the class int, and sort of it followed that calling the class would mean constructing an instance of the class, so that if you had simple code that wrote int left paren some expression right paren, it would work exactly the same way. It would have the same effect, but the workings inside were completely different. There was one particular file that sort of implemented the sort of the basic functionality of types in the language, and in Python 1 it was like 50 lines of code, and at some point I rewrote it and it was 5,000 lines of code.
That's some growth. What about types in Java?
So I've got this long history of caring about things like performance and building robust software, and often that comes out of, I'm much more worried about what it takes to build production quality software than about what it takes to just do a quick thing. And Java is not a great language for quick things, but it's for me, one of the things that I love to do, and maybe I'm weird, but being able to do automatic theorem proving on hunks of code, and a type system is a really great hook to be one of the foundations of theorem proving. And theorem proving for hunks of code turns out to be really useful for things like building optimizing compilers and doing ahead of time correctness checking, trying to be able to theorem prove away as many things as possible. So one of the not well-known things about Java is that, in the Java spec, it says array subscript checking is always on. But it's only conceptually always on, right? The truth is that there's more than enough hooks for the compiler to theorem prove away almost all index checks. And same thing with null pointer checks and all kinds of things that look like they're heavyweight, but they're really cheap. So one of the things that I really cared about at the time was that A plus B should almost always be at most one instruction. Bonus points for 0 instructions.
Makes it a lot faster.
Well, the thing about 0 instructions is often you can fold them into some weird addressing mode, right?
Yeah.
And so in kind of the universe I tend to live, being able to look at A plus B and realize it's that instruction, that all feeds off of the type system. And sometimes you can do this with sort of optimistic just-in-time compilation, and depending on how far you want to push that. So the JavaScript engine in Chrome is absolutely astonishing for the kind of gore that they go through to optimistically compile JavaScript code. But it's also very hard to do those kinds of tricks if you're trying to get into small footprint devices. There are Java compilers that work for machines that only have 50K.
Right. And
to do that kind of compaction and distillation, you need every kind of hook that gives you every last drop of information. And the earlier you know it, the better a job you can do.
Right. So Anders, speaking of lots of information that one gets, TypeScript gives you a lot of flexibility and power. What's your general view about typing?
Well, let me actually, it's funny that you mentioned CPU cycles and counting how many or whatever. I remember when I wrote Turbo Pascal, which was all written in C80 assembly code, and back in those days, you could literally look up the Intel manual or the Zilog or whatever, you know, and see how many clock cycles every instruction took, and actually it would work out just like that.
I remember.
And now, everything takes 0 clock cycles except when it takes 1,000 clock cycles. When you hit the memory wall, and it is absolutely impossible to reason about how CPUs execute your code today. That's just one.
Well, it's not impossible.
No,
it's
it's
just
not, but it's much harder.
Oh yeah, but it is a complete pain in the ass.
Yes, it is.
And they don't give you manuals that
No,
are good enough,
no,
right?
no,
If you want to
no.
actually understand it,
It's
you
great.
need to get the chip diagrams.
Yeah. But with respect to types, I've always worked on programming languages that have type systems, but it's interesting how it's gone from being type systems for the code generator's sake, or type systems for you know, generating errors, to now I almost view type systems as a tooling feature. And that's really sort of the thing that has been the interesting high order bit for TypeScript. It is, you know, first of all, starting with a dynamically typed programming language like JavaScript, and then trying to add a type system on top of it that faithfully reflects the semantics of the programming language. And the reason we're doing it is actually not because we think type systems are interesting, but because if you think about what it is that powers programmer productivity today, like everyone loves their IDE, like whatever IDE you're using. I hope it's Visual Studio Code, but but if it's not, you know, I am sure you're all like accustomed to things like statement completion and refactoring and code navigation and code definition and so forth. And if you think about it, the thing that powers that is semantic knowledge of your code. And the thing that provides the semantic knowledge of your code is a compiler with a type system. And once you add types, you can actually dramatically increase productivity, which in some ways seems counterintuitive, right? I thought like dynamic languages were easier to approach because you got rid of the types, which was like a bother all the time. Well, but it turns out that you can actually be more productive by adding types if you do it in a non-intrusive manner, and if you work hard on doing good type inference and so forth. You know, so.
Larry,
Yeah, so I wanted to jump in here.
Yeah, let's let Larry jump in and then whoever you can.
I'll probably take over the
So I really believe in that point in the power tools for power geeks thing. And one of the things that drives me nuts is the real menus VI movement. And you know, it's really, I just want to punch people who are like, I'm a real developer because I use VI. And it's like, you know,
because I do it the hard way.
I think IDEs make language developers lazy.
Wow! Would you like to expand on that, Larry?
IDEs let me get a lot more done a lot faster.
Okay.
I mean, I'm really not into proving my manhood. I'm into getting things done.
Case in point, but I'm going to take the devil's advocate here for a second.
Emacs.
Something like Emacs, okay, yeah. The Jupyter notebooks. A lot of science people, data scientists get a lot done in actually a pretty simplistic IDE with a dynamic language most of the time. So
You could get a lot more done.
I don't know.
No, but I think types have, I mean, it's not just, a type system can help you, first of all. If you're uninitiated and you want to know, well, here's my foo, and now I say foo dot, and then the IDE can show you, what can I type next, right? As opposed to I gotta go read manuals and figure it out or know it all, right? I mean, the original developer of whatever piece of code might know it all. But then people move on, new people come in, you know, here's this project. There was no documentation written about it, and if you think about it, types are documentation too, right? I mean, and they're just, there's so many things about like like adding them that down the line give you increased productivity.
Okay, so there's productivity, and then
Yeah, but
there's
that's-
maintainability,
Oh, well, both.
and maybe any different thoughts about
I didn't get to
maintaining
talk
something?
about types yet.
Oh, well, talk about types. We don't want to leave Perl types out.
Well, the story is very different for Perl 5 than Perl 6. Is the thing. Yeah, as you know, Perl 5 just sort of grew over time, and the whole idea was sort of a ticklish idea. Everything, you can pretend everything is a string, even if it's a number or a floating point internally. It's just all, you know, interchangeable. And that works out for bootstrapping people into a language quite nicely. And it's a feature that we wanted to keep in Perl 6, but what we discovered in Perl 5 as part of the redesign was it's fine if the new user is confused about the interchangeability of the allomorph, to use a technical term, of your scalar types. But it's not so good if the computer is confused about these. You know, the Perl 1 engine was written way back in the dark ages when you had to shoehorn a bunch of stuff in, and it cheated a lot. So part of the redesign, when we did the whole Perl 6 thing, we wanted to do object-oriented programming better than these languages, and we wanted to do functional programming better than most functional programming languages. To do that, you have to have a fundamental, very sound type system, a sound meta-object model underneath, and you really have to take seriously these slogans like everything is an object, everything is a closure, in Perl 6, even loop blocks are closures, and you got to optimize hard to get them away from there. But I also agree with this idea that the types also are a cultural. I talked about pegs, hanging things on pegs. They're one of the pegs. We didn't have something to hang on in Perl 5, and now we can hang all the meta information, and they can just run a little program, and they don't even have to have an idea. They can say, oh, this object dot methods dot what, they can do their own introspection of the whole thing, and people just do that all the time. By the way, we do also have an IDE.
Good points all around. So most of the time, programmers actually spend maintaining code versus writing new code out in the wild. And what things or elements of a programming language make it easier to maintain code? And maybe we'll start with Guido.
Well, I found that TypeScript is actually incredibly useful, and so we're adding a very similar idea to Python. We're adding it in a slightly different way because we have a different context.
I'm sorry, I turned my chair because my neck was like
Turn that button all the time.
somehow we're sorry. All right.
It's the ghost.
Anyway,
Oh, wait, I'm tired.
I sort of learned a painful lesson that for small programs, dynamic typing is great. For large programs, you have to have a more disciplined approach, and it helps if the language actually gives you that discipline rather than telling you, well, you can do whatever you want.
That was part of our scale-up idea for Perl 6, that the types would help with programming at large, because we did notice those limitations of loose typing.
Yeah. 1 year ago, I started working really heavily on refactoring engines, and being able to do like large scale refactorings on like millions of lines of code at once, and that really changes the way you think about maintaining code. Because the world is filled with libraries that have things like stupid variable names, stupid method names. Because, when you started out, it meant one thing, but now you realize that you really didn't really understand what you were doing in the beginning, and so this method name really should be different. But nobody ever renames methods because it's really hard to go over a piece of code and rename exactly the right variable. But if you've got a good refactoring engine, you just type, meta control R, type in the new name, hundreds and hundreds of files later, which takes about, maybe 30 seconds if it's a lot of files, you're done.
And so you basically rewrite volume 1 of the 7 volume series.
No, but this is actually like you're describing. In a sense, what was the genesis of the TypeScript project, which was these enormous JavaScript code bases that we were seeing customers, right, and in-house projects, and they were getting bigger and bigger because JavaScript engines were getting good enough for you to write really big programs. But maintaining them was impossible because it turned into write-only code. You dared not touch it once you'd written it because it worked, but there's this property called text, and I really want to change it to be, I don't know, like some other name. Except there's like a million other properties called text, and if I just do a global search and replace for text, then oh my god, it's like it all, so I can't change anything. But if you have semantic understanding of this property called text is different from that other property over here called text, and if you want to rename this one, that doesn't mean you want to rename that one. But that takes for something like a type system to be in place. And once you start adding that, you add documentation to the code and you add these capabilities where we're now seeing people with regularity refactor hundreds of thousands of lines of JavaScript code, in minutes. And it just works afterwards, and people are amazed that it's possible. But it's true that it takes a bit more work to begin with, and it's maybe not right if you're writing 5 lines of code. Okay, that may be more bother than you really care to, but it starts to pay off pretty quickly.
Find that in addition to types, really good lexical scoping helps with refactoring. It fits back into this. What's the right peg to hang this on? And often it's lexically scoped or dynamically scoped somehow, and they're doing those right and not interfering with threading and all sorts of interesting questions.
So I'm going to throw one more question out before the break in 3 minutes, and we made sort of a reference to Donald Knuth, one of the Turing winners, in this last section of conversation, and he wrote, "Premature optimization is the root of all evil." So, what's your approach to optimizing code and gaining efficiency, say in Python?
Well, I'm terrible at that, so I leave it to others.
That is spoken like a very wise language creator.
And they've lived up to the task. I mean, Python's hash table implementation has been rewritten so many times. I don't understand any part of it. But it is so much better than the thing I actually copied out of Knuth 30 years ago.
You copied it out of Clue? Oh, Canoe. Oh, okay.
Yeah, so I kind of 50% believe that, because there are, the premature optimization in terms of algorithms and code, that part of it I believe. But, people often don't really think about the role of data structures in optimization. And if a data structure is exposed, you have to, and you decide that, this algorithm is a problem, but the reason that it's a problem is because, this data structure was just slapped together and they thought, there'd only ever be 10 items in the list or 10 items in the set. and then you start, having, million item sets all the time, and all of a sudden, your little linked list is not going to hack it, right?
Or a Unix directory.
Or a Unix, or yeah, and so if you can, it's like, hide early, hide often, right? Never tell the truth about what your data structures are.
And on that note, we're gonna take. You want to quick?
No, I just wanted to say that I think, like with anything, the important thing is to make sure that you actually have the right data before you start optimizing, right? But too often you have a hunch that, oh, I think if I need to do this, I need to change this data structure from being a linked list to being an array or whatever. But if you measure, then you discover it doesn't matter. But really, there's this other thing that you haven't even thought about that matters enormously, and maybe you should go look over there. So use a profiler, figure out where is the time actually spent. I am continually surprised, and I write compilers for a living, and I'm always surprised about where time is spent.
All right, and with that, we're out of time for this section. We're going to take a quick 15-minute break. When we come back, the really hard questions are going to come out because the audience questions that have been submitted are going to be the ones that we move into. So thank you. Woo! Guido, James, Andrew, Larry. You guys have been wonderful.
And each and every one of you has a community that is formed around the languages that you've created. I'm curious if you would talk to ways in which you've seen the design choices you've made for your language shape the communities that have formed around those languages.
It really helps.
Well, go ahead.
It really helps if you're trying to make everybody, what's your slogan here? Everybody.
Everybody comfortable?
Anyway. I
feel valued and supported.
Make all Americans, I heard, feel like comfortable programming.
Oh, CS for all. Yes, to make.
Yeah, that was it.
Yes.
But,
the sign was a clue.
but it's not CS for all if it's just Americans.
No.
There are many underserved populations in the world, and what we've really discovered that it really helps build international camaraderie and community to have world-class, literally, support for Unicode.
Yes.
So I would encourage any language designers out there, don't do this halfway stuff with, code points. Go all graphics.
I completely agree. Guido, you had something you were going to say.
I was going to try and say that I don't know how my language design choices necessarily affected the community, but my choices about how to interact with the community certainly have affected the language design very deeply. I was somehow imbued with the importance of user-centered language design, because Python borrows a little bit from a language named ABC, which is long, but its authors had a bunch of things, right? And one of those was listen to the users. Ask the users what they think. And then you ignore their suggested solutions and you first figure out what their problem is, but you do give users a voice. And I've sort of taken that up and let the users help me design the language. And now they're ready to take over.
All was going to say, I always felt like it's important as a language designer that you don't create unnecessary work for your community, because it's very easy to, in the name of purity or whatever, go change something or strive for the perfect language. And I've always said, like, I mean, show me the perfect language and I'll show you a language with no users. You know, every language has imperfections in it, and it has them because it has evolved. And the hard part of language design is actually not version 1.0, it's like all the versions that come after, where you're trying to sneak new things in without actually causing extra burdens on people who don't necessarily care about the things that you're trying to sneak in, right? And so that's the hard part of language design, I think, is the evolution of the language. And keeping your community with you as you evolve.
Yeah, and so with Java, we like always followed that. We've maybe been a little bit excessive about it. I mean, I've got binaries that I compiled like 20 years ago that still run. And it's you know, on machines that were never invented when the code was compiled, and you only get there with crazy discipline and a tolerance for living with your mistakes. But it makes the it also ends up selecting who your users are. Because in the Java universe, pretty much everybody is really disciplined, because, you know, it's kind of like mountain climbing. You know, you don't dare get sloppy with your gear when you're mountain climbing, because it has a clear price. And you know, when you said something about Larry, you said something about Unicode. Java's had Unicode since '92, so you know, it's, you know, trying to be inclusive of, yeah, and that really made a difference. I mean, lots of folks thought it was like the lamest thing ever, but that was during my you know, Lord of Java phase, which yeah. But that phase of my life ended in about '95.
I'd like to say something about the stability thing, and as it relates to community. And that is, we did this try to do perfect backward compatibility thing all the way up through Perl 5, and did a really good job with it. It's one of the most stable things. There's still Perl 1 programs out there that run. That eventually runs into the problem that, you know, you can't fix your mistakes. So one of the mistakes that we made was kind of a meta mistake, and that was assuming that you had to always have that kind of stability and not change anything. How would it be to design a language where the language itself could be evolved from within by the community and be the language we want 25 or 50 years from now? This ties into what Paul Graham was talking about, a 100-year language, and we kind of took that seriously. What is it that prevents languages from evolving? Not having things go right, but fundamentally, the Perl 6 compiler is written in Perl 6. Most of the runtime system is written in Perl 6. The users can extend it. Perl 6 itself does not care whether things are built in or not. It all works the same. So most of the built-ins are written as if they were user code. So users, even if we say, no, we don't want that in the language right now, but put it in a module. You can turn classes into monitors with about that much code. You can implement an actor model in classes with about that much code. You can mutate. Adding operators is just trivial. When it does everything perfectly one pass. It drops into the subcompiler, and with the end it comes back out. So there's never ever any ambiguity as to what language you are in. And so because the
the scoping of the exact language you're in is always lexically scoped. Any lexical scope can say, use whatever language I want. A future version of Perl 6, you can say use COBOL, use Python. If someone, well, actually, people have written Python parsers in Perl 6. I don't think anybody's written a COBOL parser yet. But we'd like to think that you know, all languages are sub-languages in Perl 6 now. So I think that they're modulo semantics, which are hard. I agree. Semantics are hard. But I think there is a way forward. I think there is a way forward to get the stability and the evolution. And I think we're trying to do that.
Awesome. Do we want to take another audience question? All right. Thanks.
Hi.
Can you talk into the mic like you're eating the mic?
Hi. Yeah. Can you hear me?
Yeah.
Great. There's been a lot of talk tonight about the evolvability of languages and the trouble with implementing things that might not be backwards compatible. What's something that you wish you could have implemented with your language, but for that or maybe another reason it wasn't possible?
Well, I have a feature that I am sort of jealous of because it's appearing in more and more other languages. It's parent matching. And I cannot come up with the right keyword because all the interesting keywords are already very popular method names for other forms of parent matching.
Naming's hard.
Well, I'll go. My favorite is always like the $2 billion mistake of or the $1 billion mistake of having null in the language, and since JavaScript has both null and undefined, it's the $2 billion mistake. But I mean, if and I mean, what's done is done, right? And now you know, I spend a significant portion of my time actually working on ways to make code null safe. And who in here has ever had a null pointer exception, right? I mean, there you go. It is by far the most problematic part of language design, and it's a single value that that if only that wasn't there, imagine all the problems we wouldn't have, right? If type systems were designed that way, and some type systems are, and some type systems are getting there, but boy, trying to retrofit that on top of a type system that has null in the first place is quite an undertaking.
The features I wanted to add were negative features. I think all of us as language designers have borrowed things. You know, we all steal from each other's languages all the time. And often we steal good things, but for some reason we also steal bad things. You know,
like what?
Like regular expression syntax.
Oh, yeah. I'll give you that one.
Like the C precedence table.
Okay, another.
Okay. These are things that I could not fix in Perl 5. And we did fix in Perl 6.
Okay. Awesome. All right. We do seem to be doing pretty well with the audience. So how about another audience question?
Hi, hello there. Well, what I wanted to ask is, you can sort of notice this sort of pendulum effect in regards to tech and programming throughout time. There's been like several different paradigms. There's a certain time where people were like, are we gonna do things imperatively? Are we gonna go object-oriented or functional? And for example, right now, there's a whole bunch of languages that are sort of like very aggressively taking that standpoint of being very pro, being friendly with concurrency, or being very over-jealous about immutability with memory. And I think that that kind of pendulum effect happens because technology has actually been evolving throughout time. Our machines are like beefier and we have more memory now. So the ways that we design programming languages now are probably a lot different than they were 20 or 30 years ago. So considering that, where do you think, or how do you think the programming languages of 10 years into the future are going to look like? Or in your opinion, where is language design headed to, like in the future?
So my favorite candidate for that is that these major breaks and things like that always happen because something major happens in the underlying technology, and one of the areas of underlying technology that is kind of like a computer that I think is really underserved is writing code for GPUs. Right. I mean, right now there are no languages worth a crap, and that's a technical firm trademark, that work well on GPUs, and maybe because there's like a limited number of algorithms that people are willing to are really interested in, but they're really important ones, or maybe it's because they're inherently all mathematical, and the number of people who care about writing numerical code is small. I'm one of those, though, and so every now and then I spend time thinking about, what would you do to make GPU programming really easy?
We need a champion in Perl 6 to hook up our vector operators to GPUs.
Yeah, but it's more than just vector operators. I mean, that's kind of my problem with the whole thing, is that most of these things are just libraries of hand-coded assembly that do vector operators. And surely there's something more clever than that.
Maybe I'll just add with language design. One of the things that's interesting. You look at like all of us old geezers sitting up here, and we're proof positive that languages move slowly. And I mean, it's not, like a lot of people make the mistake of thinking that languages move at the same speed as like hardware or like all of the other technologies that we live with. But languages are much more like math and much more like the human brain, and and it all evolves slowly, and we're still programming in languages that were invented 50 years ago. Like all of the principles of functional programming were thought of more than 50 years ago. I do think one of the things that is luckily happening is that, like as Larry said, everyone's borrowing from everyone, and languages are becoming more multi-paradigm. Yeah, I think it's wrong to talk about, oh, I only like object-oriented programming languages, or I only like imperative programming or functional programming. I mean, it's important to look at where's the research, or where's the new thinking, and where are new paradigms that are interesting, and then try to incorporate them, but do so tastefully, in a sense, and work them into whatever is there already. And I think we're all learning a lot from functional programming languages these days. I certainly feel like I am, because a lot of interesting research has happened there. But functional programming is imperfect. And no one writes pure functional programs. I mean, because they don't exist. So it's all about, like, how can you tastefully sneak in mutation in ways that you can better reason about, as opposed to mutation and free threading for everyone, and that's like just a recipe for disaster, right? So.
Yes.
All languages are imperfect. Let's just settle it right there,
We've been thinking a lot about the parallelism concurrency issue. This is one of those issues where we were waiting to be smarter. We did borrow, steal a bunch of ideas from Haskell in terms of lazy lists and things like that. But in terms of how you actually are going to deal with the end of Moore's law, or if not the end of Moore's law, at least you know, multiple CPUs, many cores. When you got 1,000 cores, what are you going to do with them? And so a lot of our early design on Perl 6 was, we didn't understand how we wanted to do it yet, but we knew very deeply that we didn't want to do anything that would prevent it. So a lot of the early design decisions were you know, just saying, well, we have to keep this open. Then when the right smart people came along, they said, look, what you really have to look at is things that are composable. Threads are not composable. You can't take 2 threads and turn it into a 3rd thread. What you want is things like we stole from Go, we stole promises and channels. From C#, we stole functional reactional programming. And with these sort of primitives, which end up being duals of your regular list processing kind of primitives, they just happen to be working on events, and you can have loops, event loops that work just like regular loops, except they're running on and same control flow, so that is easy to learn. There are ways of sneaking these things into a language, at least in the ways that we understand right now. That I heard, who was it talking about adding fibers to their runtime? I think it was a Java news item. But lightweight threads that can, as Erlang has shown, you know, you can run 100,000 threads in your process.
That's another language that's been around for a long time.
Oh yeah, and we stole from them too.
Yeah.
We like their pattern matching.
Yeah,
but
well, one of the meta theorems is that all good language design is theft.
Of course.
Oh, yeah.
Yeah.
So yeah, I mean, we're thinking about it. We don't have all the answers yet, but I think all these languages, you know, long term, tend to converge on similar solutions.
So very sadly, we are at the last question. I know, it went so quickly, and unfortunately, all good things must end, except for maybe good languages. So I'm going to start and maybe quickly wrap up. As you look back over the long lives of the languages that you've written, what have you found most rewarding?
The people.
The people?
By far.
Absolutely.
Oh, yeah. I mean, that's what keeps me coming back to work every day, is like the incredible excitement that the community shows you, and I am so grateful for all the people who have used this. I mean, there's nothing more rewarding than have people just like on Twitter or wherever it is go, oh my God, this is so great, and it's like, yeah, that makes you want to just keep doing more of it. I mean, it's.
Oh yeah, when somebody comes up to me, in the street somewhere and says, thanks for giving me a career, can I have a selfie? That's this kind of like, light and dark thing. But
being famous
it's really wonderful.
Being famous is not all great. I mean, it's happened to me in Silicon Valley, at a movie theater, at a tire shop. You're Larry Wall.
Yeah, well, what's really weird is when your kids are with you when that happens.
But yes, it's when people said, you gave me a career, you gave me a livelihood, you fed my family.
Yeah.
That's the best.
I'm speechless.
And not just, we're not talking about a star relationship here of each of us to those individuals. We're talking about the second order community 2.0 kind of effects. It's one thing to see them, getting help from you. It's another thing to see them helping each other. That's a whole level above even the individual relationships, I feel. To see a community that is learning how to love, kind of building a little bit of heaven on earth. There's just nothing like it.
Completely agree. Guido, you get the last word. And we love learning from you as well. And with that, I want to say we've all learned so much from all of our wonderful panelists tonight. I want to thank you for allowing me to share and celebrate this moment with you. The little 5th grade kid in me that was plinking away on BASIC at Bell Labs, who later watched the PC, cell phone, internet, web, and cloud computing change our world, never dreamed that I would be chatting with 4 individuals who profoundly impacted our world by doing what they love, creating and building languages. Please join me in a huge round of applause to thank Anders, James, Larry, and Guido for inspiring this evening.
Thank you, Carol.
Okay, was that epic? So, Lorena, I have an idea. If you guys could step down right here, we're gonna get a giant picture of everybody. You guys stand right there. Lorena, get up here with your camera. Woo! All right, we're getting a picture of everybody in that room. All right, I need some excitement. Woo! Oh my God, I met my idol. Can you ask permission if I step on a chair? She can stand on the chair. You can use my shoulder. Stand up. Okay. All right, show some excitement, people. Let's see it. Woo!
Louder, hands up.
Come on!
All right, because 3 times is kind of weird and lucky.
Woohoo!
We did it.
Okay. Thank you, everyone, for coming. Thank you to all of our speakers. Thank you to our organizers. Let's do something equally awesome next year. And if you want a robot, they're $100, so come see me.